Hi, I'm Bhavya, and I've been working with my teammates Andrew, Caroline, and Yankolanga on improving the current UVC disinfection system for N95 masks. Due to COVID-19, there's a shortage of PPE in low-resource communities. N95 masks, commonly used by clinicians, are currently single-use. Thus, we were tasked with improving the current prototype of a UVC disinfection system that decontaminates N95s for reuse. We came up with 6 design criteria. The first is mass reusability, as reusing masks is the purpose of the system. This will be measured based on the number of mass reuses before the filtration quality significantly decreases. We also needed to prove the system efficacy, which is dependent on proving that the viral count on the mask significantly decreased after the UVC disinfection treatment. The system also has to be durable, which will be measured based on the number of disinfection procedures that the system can complete. The fourth design criteria is the system efficiency, where we want to minimize the disinfection time so that daily clinician life is not hindered. Finally, we also need to consider safety and cost, measured by the amount of UVC exposure recorded near the device and the cost of the materials, respectively. After identifying our design criteria, we decomposed the problem into smaller chunks to facilitate brainstorming and to also make the design process more manageable. To keep our brainstorming user-based, we specified the steps that a user of the system would follow. We also broke down the functions that the design must complete in order to successfully clean the masks. Decomposing the problem forced us to think creatively about each specific component of the system. After decomposing the system, we focused on brainstorming ideas for specific functions. Because the prior model was expensive and not durable, we've considered designing a disinfection box with reflective surfaces and UV bulbs on the corners. By decreasing the size of the device, the cost goes down and the lamps are held more sturdily. A different idea centered around testing the filtration of the mask post-disinfection is a smell test. If a person wearing the N95 mask has a smelly chemical sprayed near them and they can detect that smell, then the mask does not filter properly. We also wanted to make sure that all parts of the mask were being hit by the UV light, so we came up with a rotating baby mobile of N95 masks. We also wanted to integrate feedback mechanisms where there could be a red light illuminated when the UV disinfection is in progress and a green light illuminated when the procedure finishes. This could also be shown on a phone app with an alert. Finally, another improvement could be considering different power sources like solar or battery-powered systems, since some hospitals, especially those in rural settings, don't have reliable electrical power. After talking to a variety of stakeholders, designers, engineers, and clinicians, we gained a lot of feedback about the system, or brainstormed ideas, and different aspects of the system that we had not addressed. One of the key pieces of feedback that we got was that the system should be flexible for different settings. Making the system smaller, as we had suggested, was well received, but clinicians also mentioned that other larger hospitals will need more masks cleaned per day. The stakeholders we spoke to also liked a rotation mechanism to ensure that all parts of the mask were being exposed, as well as a smell test to give clinicians confidence that the mask filtered properly. The user feedback mechanism was something that designers and clinicians alike really wanted in the system, as it would make it a lot easier to use. As for concerns, many wanted a concrete test of reduced viral load and wanted to ensure that there was no risk of cross-contamination between the masks of different individuals. Now I'll pass it on to Andrew to talk about our suggested improvements.
After these past few weeks of research, brainstorming, and stakeholder interviews, we have come up with 4 suggestions on how to improve the current system. After considering the 2 different iterations of the prototype, the symmetrical orientation with PVC pipes and the circular clothesline surrounding a central bulb, we decided to incorporate aspects of each model. We liked how the circular model could clean so many masks per cycle, but also realized the benefits of the stability that the PVC model provided. We suggest changing the shape of the system to a half-circle design. In this design, there are 2 corner UV bulbs and 1 central bulb. A clothesline or PVC rack would be in a half-circle-like shape around the center bulb. The curve of the rack and the positioning of the corner bulbs could be adjusted to optimize UV exposure. The clothesline or PVC rack would have multiple layers so that more masks could be cleaned in one cycle. This shape change would decrease costs by using fewer lamps and ballasts and would cut the size of the circular system in half, all while using a similar assembly to the 2 current models and maintaining the number of masks that can be cleaned per cycle. Based on stakeholder feedback, one of the main takeaways we had was to ensure that there was a concrete test to prove both that the masks had been disinfected and that they were still filtering properly. To address this first concern, we suggest having a viral load test based on dosimeter card readings. After setup of the system, a UV meter would be used to measure which mask receives the least exposure. A dosimeter card would be placed near the mask, and the card will indicate the dosage that the mask receives. If the card receives a 1 joule per centimeter squared dosage, then the users can assume that every other mask has received the proper dosage as well. To address the concern of maintaining mask filtration quality, we suggest implementing a smell test. This test has been approved by the Occupational Safety and Health Administration as a way to test the filtration of N95 mask respirators. By aerosolizing different smelly substances, such as isoamyl acetate, which smells like bananas, these chemicals can be sprayed near a mask wearer. If the person does not smell the substance, then the mask is filtering properly. The stakeholder feedback we received also encouraged us to implement feedback mechanisms into the current design. We suggest adding a red LED to show when the system is in progress and a green LED to show when it is finished. This can be connected to a power strip or one of the ballasts as an output of the system. Our last suggestion to the current system is to have a screening process that takes out soiled masks. Cosmetics, lotions, and other makeup products block UV radiation, and thus these soiled masks are not properly disinfected. We urge clinicians not to wear makeup while using the N95s, but we also suggest having a thin, breathable fabric that can be put inside the N95 mask and could be later discarded. Thus, the makeup will only reside on this fabric and will not interfere with the mask itself. We expect that our suggestions will help the system meet many of our design criteria. The mask will still be disinfected for the necessary 5 uses as suggested by literature, and the viral load test will ensure that 99.9% of the virus is killed. The durability of the system would require further testing once the system is in use. The system would still take around 22 minutes per cycle, and this would be measured based on the illumination of the lamps and the 1 joule per centimeter squared dosage that is required. Considering safety, there should be no exposure to UV radiation outside the room where the system resides. Finally, by adapting the orientation to use fewer UVC bulbs and ballasts, the cost will decrease by around $230, meeting our ideal range. With these suggestions, we also realized that this system is not one that is applicable to every environment. These disinfection systems are not one size fit all, and thus we have 2 future project proposals to expand upon the current prototype. First, we propose a project to design a small UVC box that will not take up a whole room, but rather would be smaller, more affordable, and more portable for rural settings with less financial capital. Potential ideas for this project include having smaller bulbs, adding reflective surfaces, creating a solar power source, and adding feedback mechanisms. When researching the specifics of the UV disinfection system, we realized the importance of having a functioning UV light meter to ensure that each mask is receiving proper illumination. UV light meters are currently sold for between $700 and $1,000, making them inaccessible to low resource settings. After researching some designs for homemade UV light meters we believe that is well within the scope of a RICE 360 project to design an affordable, durable UVC light meter for use in low resource settings. Finally, we wanted to give a huge thank you to everyone who has helped us out through these past few weeks. Thank you.